Not in the ticking of clocks, but in the slow, unbroken drift of existence itself, a river without source or shore. It carries the stars through their burning youth into their dim, red twilight. It pushes galaxies apart like autumn leaves caught in a current. It draws every life from its first breath to its final silence, never pausing, never looking back. This is the river we call time. To human senses, it feels absolute, a forward march written into the very machinery of the universe. The sun will rise tomorrow because it rose today. The cup that shatters will never leap whole into the hand again. Ashes will never become flame. And yet, what if the current could turn? Imagine the impossible. Shards of glass reassembling mid-air into a perfect pane, the echoes of music rushing back into the instrument, burnt paper unburning into crisp, white sheets. In the heavens, stars collapsing into clouds of unspent gas, planets spinning backward into the swirl of their creation, the entire cosmos rewinding like a vast celestial film reel. Science calls this the arrow of time, a direction born not from inevitability, but from the order and disorder of matter and energy. But in the deep mathematics of physics, there is no law that demands it must always point the way we think it should. So the question emerges, silent and unnerving: is time's flow an unbreakable truth, or a fragile illusion, held together by the current state of the universe? And if that illusion falters, could the river turn, not in myth or dream, but in the very fabric of reality itself? Somewhere, hidden in the quantum weave or the curvature of space-time, might time already be running the other way? Humanity's understanding of time has always been bound to observation. From the slow sweep of shadows across stone to the rhythm of moons and tides, the forward march of events has been the single most reliable feature of reality. But in the early 20th century, something began to crack in this certainty. It started with the birth of modern physics. Isaac Newton had long described time as absolute, a universal stage upon which events unfolded in an orderly sequence, the same everywhere, forever. But in 1905, Albert Einstein shattered that notion. His theory of special relativity showed that time was not a universal constant but a flexible dimension, one that could stretch, slow, or even stop depending on speed and gravity. Suddenly, time was not a fixed backdrop. It was part of the fabric of reality itself. Einstein's later work on general relativity deepened the strangeness. The geometry of space-time could bend, twist, and fold under the influence of mass and energy. Time was no longer merely measured, it was shaped. Meanwhile, in the microscopic world, quantum mechanics introduced equations that treated time not as a relentless march forward, but as a parameter that could run in either direction without breaking the math. The Schrödinger equation, for instance, is perfectly time-symmetric. If you film a quantum process and play it backwards, the equation still holds true. This symmetry troubled physicists. Why, if the fundamental laws didn't prefer a direction, did reality itself seem so one way? Why did we remember the past but not the future? Why did entropy, disorder, always increase? In the mid-20th century, experiments in particle physics hinted at cracks in this forward-only dogma. The discovery of CP violation, a subtle asymmetry in the decay of certain subatomic particles, suggested that the universe had a slight bias toward one temporal direction. But that bias was small, almost vanishingly so. It raised a new question. If the laws of physics allow time to move in either direction, could there be realms, or even entire universes, where it runs the other way? The possibility of reversed time struck at the heart of both physics and philosophy. It was not merely a technical curiosity, it was an assault on the foundations of cause and effect. Consider the simple act of striking a match. In a reversed time universe, the blackened stick would gather glowing ash into a flame that drew itself back into the head of the match, which would then unstrike itself against the box. In our world, such events feel absurd, yet in the realm of pure equations, they are entirely permissible. This dissonance between mathematical symmetry and human experience was deeply unsettling. Ludwig Boltzmann's statistical interpretation of thermodynamics had given rise to the concept of the arrow of time, the idea that entropy inevitably increases. It was this one rule, above all others, that seemed to dictate time's direction. And yet, entropy itself was not a law written into the fundamental equations. It was a statistical outcome, a tendency, not an unbreakable command. Physicists realized something disturbing. If entropy could decrease, even locally, time's arrow could, in principle, reverse. This was not merely academic. The early universe, immediately after the Big Bang, was in an extraordinarily low entropy state. As it expanded, entropy rose, giving us the arrow we know. But what if, far in the future, conditions allowed entropy to fall again? Could the universe itself turn around? The shock deepened when cosmologists considered the symmetry of spacetime itself. Solutions to Einstein's equations allowed for closed time-like curves, loops in spacetime that would permit travel into the past. Though these solutions were exotic, often requiring impossible conditions like negative energy, they were not forbidden. Nature, it seemed, might not share our prejudice for the forward flow of time. To probe the true nature of time's arrow, scientists turned to the cosmos itself. The cosmic microwave background, the faint afterglow of the Big Bang, provided the earliest possible snapshot of the universe. Its uniformity told a story. From near-perfect order, the universe had tumbled into ever-growing complexity and disorder. But that starting point was an anomaly. Why had the universe begun so improbably ordered? Roger Penrose argued that this past hypothesis, the assumption that the universe began in a state of low entropy, was the single fact that explained time's arrow. If the initial conditions had been different, the arrow might have pointed the other way. In particle accelerators, experiments in quantum systems revealed something equally strange. At very small scales, certain systems could be reversed almost perfectly. Ion traps and spin systems could be manipulated to rewind their quantum states. Though these reversals happened in controlled conditions and over microscopic timescales, they hinted that reversal was not inherently impossible, only improbable on large scales. Astronomers also explored the far future. Models of cosmic expansion showed that, if dark energy's influence changed, the universe might eventually contract instead of expand. A contracting universe, as entropy evolved, could, in some scenarios, see its arrow of time reverse. Galaxies could draw together, stars reignite in reverse, light converge back into matter. The investigation now spanned from the smallest particles to the entire cosmos, with each new insight deepening the mystery. Was time's direction a fundamental property, or just an accident of our current conditions? The deeper the search, the more unsettling the possibilities became. If time could reverse under the right conditions, then the now we inhabit might not be unique, it might simply be a midpoint between two opposing flows of time. Some cosmological models, like the Janus universe, proposed by physicist Julian Barbour, imagine time flowing in two opposite directions from a single low-entropy origin. In one direction, we move forward as we experience it, in the other, another universe flows backward relative to ours, though its inhabitants would perceive themselves as moving forward in their own arrow of time. This raised profound questions. If such a twin universe exists, is it in our past, our future, or both? Could its reversed flow ever intersect with ours, creating zones where time appears frozen or chaotic? In black holes, the nature of time became even stranger. Near the event horizon, time for an outside observer slows almost to a stop. Inside, classical physics breaks down entirely, and some solutions to Einstein's equations suggest that the singularity might connect to another region of spacetime, perhaps one where time's flow is inverted. Each discovery seemed to pull at a thread in the fabric of reality, suggesting that time was not a single, unbreakable arrow but a patchwork of possible directions, stitched together by the evolving geometry of the universe. The speculative landscape of reversed time is rich and varied. Thermodynamic reversal. In a closed system where entropy decreases, the arrow of time naturally flips. The challenge is finding a mechanism in the real universe that could sustain such a reversal on large scales. Quantum time symmetry. At the quantum level, processes are often time-symmetric. The two-state vector formalism even treats the present as determined by both past and future boundary conditions, suggesting that causality may not be as one-directional as we think. Cosmological bounce. In some models, the Big Bang was not a singular beginning but a bounce from a previous contracting universe. In the contraction phase, time's arrow might have flowed in reverse relative to ours. Multiverse time directions. In a vast multiverse, some regions could have reversed arrows. These regions might be forever inaccessible, yet their existence would imply that our forward flow is not fundamental but local. Speculation also turns to life in a reversed time world. Would beings there perceive cause and effect differently, or would their subjective flow still feel forward to them? If time's reversal came to our universe, would we be aware of it, or would our consciousness itself run backward, trapping us in an infinite loop of reliving our past? Testing the arrow of time is not simple, but scientists are building tools to push the limits. In quantum computing labs, researchers manipulate qubits in ways that can reverse their evolution briefly, creating time reversal experiments at microscopic scales. These experiments don't violate the arrow of time but reveal how close it can come to bending. The Large Hadron Collider continues to probe CP violation in particle decays, hoping to uncover deeper asymmetries that might explain time's preference, or lack thereof. In cosmology, telescopes like the James Webb Space Telescope peer back toward the universe's earliest light, searching for patterns in the distribution of galaxies that might reveal clues about the origin of the arrow. Future missions, like the proposed gravitational wave observatories, could detect signatures from the very early universe, perhaps even from a contracting phase before our Big Bang. Even in black hole research, physicists are exploring how Hawking radiation and information loss might relate to the symmetry, or asymmetry, of time itself. If time can run backwards, then our understanding of life, death, and meaning must change. In a reversed universe, endings would become beginnings, and every farewell would be a prelude to a first meeting. The march toward entropy, decay, and darkness would be replaced by a climb toward order, youth, and light. Yet this would not be immortality, it would be a different kind of destiny, one where freedom and choice are bound to the path already walked. The possibility that time's arrow is an illusion humbles us. It suggests that the flow we feel is a feature not of the laws themselves, but of the conditions we inhabit. Somewhere, perhaps, another version of us is already moving in the opposite direction, watching the stars grow younger. And if the river ever turns for us, we will not see it as reversal. We will simply keep moving forward, into a future that looks like our past, carried by the same current, unaware that the tide has changed. Time, whether forward or backward, will remain the canvas on which the universe paints its story. And we, no matter the direction, will be its fleeting brushstrokes.